Hello everyone. In this session of Unit 5, we will talk about crosstalk and noise. Crosstalk and noise are very real threats and for deep submicron technology. And STA tool like prime time also gives us the functionality of checking crosstalk and noise. So we will first see what does noise mean, what does crosstalk mean, and how prime time, what methods does prime time apply to check for crosstalk and noise problems, and what are the reasons behind noise and crosstalk occurring, and why is it a newer phenomena than so earlier in technology dating back to 90 nanometer or 130 nanometer. The crosstalk and noise effect was very minimal, and even 130 nanometer and larger technologies and bigger technologies, they did not even check for it. So what is changing in lower technologies and what is causing these to become a dominant effect, we'll see. So noise is something which is caused by crosstalk. So the reason why the noise plays an important role in deep submicron is that, okay, look at this figure first. So earlier technologies, you had the metal layers were further apart, and since it was the packing density was less, the number of metal layers has been increasing a bit. So now the metal layers are packed close and close together. What this means is that, so if you compare two technologies, 0.25 and 0.13, we see that in 0.13 the metal layers are nearer there as compared to 0.25. What it means is that because of the increasing number of metal layers, higher routing density. So these are important keywords here. The increasing number of metal layers, higher routing density. We are now packing because of the lower feature size of the transistor. We are now able to pack more and more transistors on chip. What this means is that, okay, yes, we are increasing the number of devices, we are increasing the number of functions on a particular chip, but the metal layers are not scaling according to that, according to Moore's law, right? Transistors do scale according to Moore's law, but metal layers do not scale that height, right? So, but because of the increasing number of devices and increasing number of functions on a chip, the routing density is now huge as compared to, let's say, 2 or 3 technologies before. And so this means that the metal layers are coming closer and closer together. When the metal layers are coming closer together, the capacitance between them now cannot be ignored. Earlier it used to be minimal. Earlier the coupling capacitance and the capacitance between two metal layers. Earlier this capacitance used to be minimal and used to be actually very small when compared to the capacitance of the net with respect to the ground. So now these capacitances are not trivial. One more effect is that there are lower supply voltages. Lower supply voltages means the noise effect. Let's say a 0.1 volt of noise on a supply voltage of 1.2 will not make that big a difference as it will do to a supply voltage of 0.9. Right? So lower supply voltages means that now devices are more prone to noise. Also, the waveforms are faster because the frequencies we are targeting are more now. The CPU frequencies are increasing like everything. The desktop CPUs have gone beyond 3 GHz and so on. So there are faster waveforms now due to higher frequencies. All these effects, they are causing noise and crosstalk to be a dominant factor now. So this is one example where you have this net 1, net 2 and net 3. Now between net 1 and net 2, you have a coupling cap of CC1 and CC4. The CC3 is connected to net 1 to net 2, not net 1 to net 2. So CC1 and CC4 is the coupling capacitance between net 1 and net 2. If you talk about net N2 and N3, you have CC2 plus CC5. Similarly, N1 and N3 you can calculate. So these capacitances now, coupling capacitances, are now not negligible when compared to the cap with respect to ground. So the cap with respect to ground is responsible for the increasing delay, right? The net delay is responsible for the net delay. It adds to the load at the output pin of the transistor. But the coupling capacitance what it does is that it will cause an effect which is called again called crosstalk, is that the signal change here will affect the signal value here. So noise and crosstalk, they both are the causing effect is same, but noise is some, we will differentiate between noise and crosstalk in a while. But so this is the effect that the coupling capacitance is causing, is that a signal change on one net will cause something to happen on the other net. If the coupling capacitance is not there, it will not happen, right? So since the coupling capacitance is becoming more and more significant, these effects are more and more pronounced now. So effect of crosstalk. So crosstalk is, you can say the crosstalk is nothing but the non-trivial coupling capacitance, and there are two effects. One is noise, other is crosstalk. What is noise? Noise. So in both the cases, in both the noise and crosstalk delay, there is one aggressor line. Aggressor line means the one that is changing its value. Now in the case where victim line, so now this aggressor line is changing its value, and it has a coupling capacitance with respect to a victim line. So in this case, let's say for example, I can say that N1 is aggressor, N1 is changing its value, N2 is holding its value, N2 is static either at 1 or 0. Now if the change on the aggressor affects the logical value on the static signal, and if it can cause a noise or cause a logical failure, then this effect is called noise, right? What it means, let's say the buffer here, let's say the buffer here, the buffer here is driving a 0, and this the signal on N1 changes its value to 1. Now if the 1 here causes a bump here, and if this bump because the aggressor is changing to 1, it can cause the voltage at N2 to rise to a certain value, and if this bump is greater than the noise margin of this buffer here, then it can change the logic value. Ideally the logic value here also would be 0 at the end of the buffer 2 here. But if this bump here gets this buffer is the height of it is greater than the noise margin of this buffer, then the logic value at the end of this buffer will not remain 0, it will again show a bump. This is called noise. So noise is the case where the aggressor line is changing its value and the victim is static, right? Crosstalk delay is the effect where aggressor line is changing its value and victim line is also changing its value. The effect here is that the aggressor will force the victim line delay. Now the delay, when we talk about delay, we mean that there is some change in value, right? That's what delay is. So for example, a buffer delay is nothing but input change to output change, the time take. Now in this case, the victim net is also changing its value. Now this effect can make this change in value a bit later or a bit earlier. So it can cause the delay to be more or less, right? So aggressor is, see this figure here, aggressor is switching rising or falling, victim is switching rising or falling. There is a coupling capacitance of T there. So instead of this waveform, this kind of waveform, due to delay, the waveform can be like this. So in this case, it is causing the waveform to get delayed. So it will increase the delay, increase the net delay, right? So these are the two effects. So the cause is same. The cause is non-trivial coupling capacitance, and it can affect in two ways. One in terms of delay, second in terms of noise. Right? Now let's discuss more about crosstalk glitch. Glitch or noise is the same thing. We use them interchangeably for noise analysis. So steady state signal, again remember that glitch is caused on a steady state net, right? The net which is holding its value, and if a glitch is observed on that net because of the coupling capacitance to the aggressor, this effect is called glitching or noise. A steady state signal net can have glitch, positive or negative, due to charge transfer by the switching aggressor to the coupling capacitance. A positive glitch induced by crosstalk from a, so see here, this NAND gate here is changing its value, so it's an aggressor net. There is a coupling capacitance CC with respect to the victim net, The 0 to 1 here can cause a rising glitch, a positive glitch at this net because of the charge sharing here at the victim net. The NAND to cell switches and charges its output net labeled aggressor. Some of the charge is also transferred to the victim through the coupling capacitance and results in a positive glitch. Right? Now, what is one thing that is most important is the magnitude of the glitch. Now, the magnitude of the glitch is that how big is the glitch? Is it big enough to cause a logical failure, or is it small enough? This is a very important factor in the consideration, because it will enable the prime time tool to check whether the noise is below or above the noise margin of the affected cell. Now, it is dependent on a variety of factors. One, obviously, on the coupling capacitance. The greater the coupling capacitance, the greater the charge sharing and greater the magnitude. The transition of the aggressor net. The faster is the slew at aggressor net, the larger the magnitude of glitch. The faster is the slew means the driver is very strong. So usually strong drivers, big drivers are very big aggressors also, because they cause a very fast transition. You can say that whether the faster transition is the cause, or the underlying cause is actually the higher drive strength of the aggressor. The victim net grounding capacitance. The smaller the grounded capacitance of the victim net, the larger the magnitude of the glitch. So you can say that it depends on the ratio of coupling cap to the ground capacitance. If the coupling cap is much more than the ground capacitance, it will be more affected by the noise. If the ground capacitance is more, obviously if the ground capacitance is more, it will help in diminishing the effect of noise, right? Then the victim net drive strength. Again, the ratio, we are talking about the ratio of the aggressive drive strength to the victim net drive strength. Usually, noise problems occur for cases where the victim net is a weak driver like X1 or X2, and the aggressor is a strong driver like X8 or X15. So, the types of glitches are rise and fall glitches and overshoot and undershoot glitches. When the rising aggressor couples to a victim net which is steady high, and steady high means it's almost at VDD, and there's a glitch which takes the victim net above its VDD value, it's called an overshoot. Again, noise that takes a victim net already at 0 to something below 0, it's called undershoot. So this figure will tell everything. Victim, if it's high, maintained high, aggressor rises, there will be an overshoot glitch. This is VDD. This value is VDD. This overshoot glitch takes it beyond VDD. If victim is falling, it might take aggressor down with it. It will take aggressor down with it, and this will be fall glitch. Fall glitch is when victim is 1 and the noise causes it to fall below 1 or below VDD. Again, if the victim is steady state low, aggressor rises, it will cause a rise bump. This is called a rise glitch. If the victim is low, aggressor falls. The fourth case, aggressor falls, it might take it below 0. It's called undershoot. Right. So 4 glitches. Overshoot is beyond VDD or beyond. So overshoot and undershoot come in the category of beyond rail noise violation. These are called beyond rail. Overshoot goes beyond VDD rail. Undershoot goes below VDD, below 0 rail, below ground rail. Other ones are rise and fall, simple rise and fall. Now, so let's say a glitch. Let's go to the figure here. Now, a very important factor in glitch calculation is the calculation first, and then see whether it can propagate. So, for example, let's see here. First thing that the tool will do, it will calculate the glitch. Let's say N1 is aggressor, N2 is victim. It will calculate the glitch at N2, and then it will evaluate whether this glitch can propagate through this buffer. So the slide here is will make us understand how this happens. So the glitch caused by coupling from an aggressor can propagate through the cell depending on the fan out cell and the glitch attributes such as glitch height and glitch width. So there are two analyses that are performed here. One is the DC noise analysis. So DC noise thresholds. This analysis only examines the glitch magnitude and is conservative. So it just takes into account what is the glitch height. Height means what is the maximum value. So there are two things with respect to a bump, with respect to a glitch. See this. Let's see the rise glitch. This is 0. This is the maximum value up to which the glitch, the bump goes. So this is called the magnitude of the glitch. The magnitude of the glitch is the maximum rise or drop in the voltage value. The width of the glitch is how much time, how much wide the glitch is. What is the amount of time during which this glitch is active. So these are two effects here. So the DC analysis only depends on the magnitude, on the height of the bump. The AC analysis examines other attributes such as the glitch width and the fan out cell. What is the fan out cell output? So let's see what all both these analyses do. So please remember, usually when you work in prime time, when you start analyzing noise, in most of the cases you will not have to do anything. You just have to enable noise. All this data, the noise thresholds and all, everything usually comes from the library, the connector library itself. The non-linear delay model is only for delay, is not for noise. Just because of there's a separate now the more popular model is CCS, the constant current source model. Now the constant current source model supports all three things. It supports delay, it supports power, it supports noise. So if you are reading a CCS enabled library, then the noise data is already present there, the noise thresholds are present there, the current waveforms are there. So after reading this library, prime time can easily do noise analysis for you, right? The only there are some cells and analog macros for which you will have to define the noise margins yourself, maybe, but otherwise the noise analysis does not need a lot of setting up to do. But it's time consuming, again, it's CPU intensive. So the DC margin is a check. If you remember the most famous waveform of an inverter output V out versus V in waveform. Now wherever there's a unity slope on these 2 points, we calculate two values, VOH min, VIL max, VOL max and VIH min. Now let's say this buffer is at a receiving end. It is into the fan out of a victim. Now the two things are important here. One is VIL max, another thing is VIL min. So DC margins are based on VIH and VIL are steady state noise limits. These can be used to filter whether and determine whether a glitch can propagate to the fan out cell or not. Right? Let's see. So anything that is on the lower side, any voltage that is greater than VIH min can cause a glitch to propagate. On the higher side, if it's lower than VOH min, it can cause a glitch to propagate. Right? So DC noise margin can also be fixed to the same limit for all nets of the design. This slide is telling us that if the noise values are not coming from the margin values are not coming from the library itself, then you can assign some values and assign them to all the nets. Now let's say I say that okay, I calculate the noise, I somehow get the noise VIH and VIL values for a particular inverter. I can use the same value for all the nets in my design. I can say that, let's say I say that VIH, let's say for our 1 volt technology, I say that both are 0.1 or 0.2, let's say. So any bump which is greater than 0.2 will only propagate. I can set this value, I can set a command called set noise margin, I can put this value for all the nets in the design. So this will check if the margin values are not coming from the library. I can calculate a conservative value and apply it to all. That's what it's recommending. That one can set the largest tolerable noise above which noise can be propagated through the cell, right? So typically this check ensures that the glitch level is less than VIL max and greater than VIH min. So the question is that will this propagate, will this particular height of the glitch will propagate to a particular point. So there is a VDD, and what we have done is that between VDD and VSS we have plotted two values of VIL max and VIH min. Now VIL max means, now this among all these cells that we are using, what is the maximum VIL for all the among all the VIL values? This is VIL max. This is not actually conservative analysis. This is you are choosing just some value, you are choosing just a maximum value. To be conservative, you have to actually choose the minimum value, right? Because you want that prime time should not filter out any noise that is greater than that is more than the least noise margin among all these things. But don't worry about it. When you do noise analysis, most in all probability you will have a standard cell library that will have individual noise margin data for all the cells. Right? So this is the case for the case where you don't have the noise margin data and you are applying some noise data margin yourself. So in this case, this gives you one methodology of applying the noise margin. Whatever be the case, how prime time analyzes is that there will be a line of VIH min and VIL max. Any glitch below VDD that is not that does not touches VIH min is okay. Similarly, any glitch beyond VSS that doesn't go beyond VIL max is safe. These will be filtered out by cell. Now, if you remember in unit 1 and 2, we talked about the CMOS. We were comparing in unit 2. We were comparing CMOS technology with other technology, with the ratio logic, with the domino logic, and so on. And we found out that the CMOS circuit is very good in terms of handling noise, and it is the case. It is the most superior in terms of handling noise, the complementary CMOS, right? So any switches which are small, so noise margins. When I say that it's most competitive at handling noise, it means that the values, the noise margins are very good. So most of the glitches are filtered out by the cells themselves, right? A small glitch, any small glitch which is below the limit will not propagate at the output of the cell. But any glitch which is higher than this are potentially hazardous. They can affect they can. So let's say now this goes to a clock reset pin, and let's say there's a noise of this kind, and this reset pin, let's say, is active high. So you have noise of this kind. So if the input is this, there will be bump here, and this will cause the clock to reset. It's very, very dangerous, right? That's why prime time will apply a filtering criteria based on the noise margin, on the DC noise margin, and it will filter out all the noise which is below this margin. Right? Now, not all glitches with magnitude greater than DC noise margin can change the output of the cell. The width is also important. That means if the glitch is very narrow, if it is very quickly it goes, so the bump, if there's a very narrow bump, so the slides talk about the difference between these two cases. Where there's a narrow bump, I'll draw it again. So now let's say the height of the bump is same, but one bump is narrow, but one bump is wide. So not all narrow bumps will go through the cell, and some of the wider, obviously the wider bumps will go through because it allows sufficient time for charge to propagate. But not all narrow bumps will go through. So the width of the glitch is also important consideration. A narrow glitch at cell input will normally not cause any impact. However, DC noise margin uses only a constant worst case value. So DC noise margin does not take into account the width of the noise. So earlier noise analysis algorithms, let's say 3-4 years back, use only the height of the noise bump to propagate the glitch. But nowadays, prime time, it also it uses AC analysis and also takes into account the width of the glitch. Right? So this is what AC threshold is all about. This slide doesn't show dark and light shades, but I'll point it out. The dark shade region represents the good or acceptable glitches. This is the darker shade, where so there is a DC noise margin, and then we have plotted the glitch height. So this is the glitch height on which we have plotted the DC noise margin, and now there is a glitch width also. So this area belongs to the glitches that have lower widths. So this is the safe area. So as the glitch height keeps on increasing, the safe area becomes narrower and narrower. That means now we are worried about the area of the glitch. So the glitches, if it's narrow but it's too tall, the area will be more. Even if it's shorter but it's more wide, the area will be more. So it becomes shorter. It stops mattering after below the DC noise margin. That means any noise, if its highest value is less than the DC noise margin, will be filtered out. But more than this, if any noise is greater than DC noise margin, Now we have to also think about the width of this noise. If the width is more, glitch width is more, you are now going into area of potentially hazardous glitch. If the width is less, you are more into safe area. What it means is that now there are two conditions that need to be satisfied for a glitch to propagate. One, its maximum value should be greater than the DC noise margin, this value here, and it should be wider beyond some threshold. The width is dependent on the AC analysis, and therefore it's a time consuming analysis, and we'll see what all DC will do to do AC analysis now. But this thing should be clear that the height and width are both important, right? The height obviously should be beyond the noise margin. The width is a separate case. If it's too low, it won't affect. If it's wide enough, it will affect. Right? Now let's see the case where the output cap is lower or higher. Now let's say there's an input without an output load, a positive glitch at its input. Now this glitch is being caused by some other aggressor, right? And if there's no load here, that means the capacitance to ground is almost non-existent. So it will have the maximum effect of the glitch, right? Assume in all the three cases that the glitch input is greater than the DC noise margin, and it will cause a glitch of the inverter output. If the inverter is driving some output load, so the glitch effect will be smaller. If it's driving a higher load, the glitch effect will still be smaller. It might be non-existent. This is because now this capacitance keeps on increasing and it keeps on going beyond the coupling capacitance. So this is the reason why it is now not a good practice to leave the output of a cell open. It can cause a big noise on this net, and although it won't affect any logic value at a first glance because it is not driving anything, but this glitch now can cause some other effect, some other coupling capacitance effect. That is why we will always make sure that any cell should not the output should not be high. It should be either grounded or tied to LED or the cell removed, right? Now there can be more than one aggressor because a net has a lot of surrounding nets, and it can have more than, it can even have 2, 3, 4, 5 aggressors. Now when multiple nets are switching concurrently, the effect is compounded due to multiple aggressors. This is one effect where there's coupling cap. Okay, this is the case where there's only single aggressor. So now for complete accurate analysis, what PT must do is that it should also so not all, let's say a net has 4 aggressors. Now what is the condition of noise? Noise condition is that the victim net should be static and the aggressors should be switching. Now do we assume that all aggressors are switching at one time, or do we assume that one aggressor is switching at one time? Our assumption will change the noise calculation if all the aggressors are switching at one time and if they are switching in one single direction. So here two things are important: the timing of the switching and the logic level from which they are switching. If all the aggressors are switching at one time and at one direction, it will cause the maximum glitch. All other cases will be less worse than this. So what does prime time do? Now please note that prime time is a timing tool. At each, because of the, for example, if you talk about register to register timing path, it knows when the nets between these two registers are switching and what is the baseline here. The baseline here is clock switching. So assuming clock switches at 0, rises at 0, it knows about all the nets in that timing path which are switching with respect to this clock, at what delay they are switching, after what time they are switching. This is called a timing window, arrival timing window. So prime time being a timing tool, at each node it knows what is the arrival timing window, and it will use that arrival timing window analysis to determine the magnitude of noise. Let's see this example. Now let's say there are 4 aggressors with different glitch heights. The glitch heights being 0.11, 0.1, 0.09, 0.2. These are in terms of voltages, and being a timing tool, prime time has the timing window information for A1, A2, A3, and A4. So consider the region 1. The region 1 has both A1 and A2 switching. So the maximum value of glitch would be 0.11 plus 0.1, it is 0.21. The region 2 has all the three of them switching, but now A3, so all the three are switching, so the magnitude is 0.11 plus 0.1 plus 0.09, it is 0.3. Between 3 and 4, only A3 is switching, so 0.2. Between 4, both A3 and A4 are switching, so it's 0.32. So this example is not talking about the direction of the glitch. That is, it is not worried about whether they are rising or falling. It is assuming that all the transitions are happening in the same direction. So this is how prime time does a timing window based calculation, and it is obviously the most accurate. You cannot assume arbitrary timing windows. The timing windows depend on the clock relationships. For example, if the clocks are asynchronous, then if the two nets, if the aggressor and victim are asynchronous to each other in terms of clock domain, that is, A is on clock domain A, let's say the aggressor is on clock domain A, victim is on clock domain B, and if clock domain A and clock domain B are on asynchronous values, then the timing window will be infinite. That means asynchronous means that the signal can switch at any time. But if both the nets are in synchronous domains, let's say if all the four are in synchronous domains, or all the four are working on the same clock, and the victim is also on the same clock, then proper timing window analysis should be done by the tool. This is the accurate way of doing things. This is why noise and crosstalk becomes so complex in terms of compute resources, right? It needs to store the timing window at each and every node. It needs to calculate the glitch on crosstalk for all such cases. That's why when you start enabling noise and crosstalk into prime time, the run times become huge, right? So this is how the timing window correlation is done. Again, there is something. Again, I said there are two effects. Actually, there are three effects that are taken into consideration. First is the timing window. Second is the functional correlation. First is the timing correlation. Second is the functional correlation. And based on this, it will calculate whether the glitch will propagate or not. So this slide was timing correlation. This is functional correlation. For multiple aggressors, again, it needs to know that now the net one N1 has coupling with N2, N3, and N3 and 4. N4 is assume that N4 is constant. Now N4, although it has coupling with N1, it is constant. A constant net cannot cause any noise or crosstalk on the other net. This effect should be discarded, right? N2 is a net that is part of debug bus. But if the chip is in functional mode, this will also be constant. So N2 effect is also not there. This is where PT needs to know about the functional values. So if you have set some case analysis on N4, if you have set some case, if due to some case analysis, now case analysis propagates. If due to some case analysis, N2 is also grounded or tied to VDD, then these effects are not taken into consideration, right? So if N3 carries functional data, and so N3 can only be termed as the aggressor for victim N1. So prime time needs to know it will use the same fundamentals it used for delay calculation. It will propagate case analysis for noise also. Make sure that none of the constant net is an aggressor, plays an aggressor. It will also take care about, it will also calculate the timing windows and worry about the timing correlation. So this was all about noise. So important things. First thing to know, what is the definition of noise? The victim net is static, it's not changing, aggressor is switching. What is important here is coupling capacitance. Obviously, all things are important. Coupling capacitance, the capacitance of victim with respect to ground, the drive strength of the aggressor and drive strength of the victim. These are the causes that can magnify or reduce the noise. Then, how does noise propagate? DC noise analysis, we worry about the bump, the height of the bump. The AC noise analysis, in addition to the height of the bump, we are also worrying about the width of the bump. Last important factor, timing correlation and functional correlation. So prime time considers, so you see now how much data now STA tool has to comprehend now. It has to comprehend the noise margin. It has to take into account the coupling capacitance. It has to take do DC analysis, AC analysis, timing correlation, functional correlation. This is why even for a small chip, a tool like prime time needs a machine with 32 GB of RAM, 16 GB of RAM. Because the amount of data is huge. There are millions of nets. There are millions of coupling capacitances to take into account, right? So now let's talk about so we were talking about noise. Apart from noise, there's also a case of delay. The delay meaning that aggressor is switching and victim is also switching. Now based on the direction of switching, the victim net can be delayed, the victim transition can be delayed or made to become earlier. This is called the delay. So okay, this is the same example where the aggressor has some coupling capacitance with net. Now different scenarios, the capacitor charge required from driving cell can be different. Now let's see this case where there is the capacitance, the coupling cap is CC, the grounded cap is CG, aggressor and victim. Now when aggressor net is steady, the driving cell from N1 net provides the charge for CG and CC to be charged to VDD. Aggressor is steady, the victim is rising, but now it has also CC in place. So it will charge both CC and CG to VDD. Aggressor net if switches in the same direction, the driving cell is aided by the aggressor switching in the same direction. If this is switching in the same direction at the time of this switching, if the timing windows overlap here, then aggressor is helping CG to switch to VDD. So it will help in the delay part. That means the delay will be less now. Case 1 is when aggressor is silent, it's not switching, there will be some delay X. But when aggressor is switching in the same direction, it will help the victim, and now the delay will be less than X. The driving cell is aided by aggressor switching, the total charge provided by driving is PG. If the slew of the aggressor net is faster than that of N1, the actual charge required can even be smaller than CG VDD, and it will help. The delay will be less than X. If the aggressor is switching in opposite direction, the coupling cap is charged from minus VDD to VDD, and the charge and coupling capacitance changes by 2 into CC VDD before and after conversion. Right? This will not help. This will make the delay more. It will make this has to now work more to charge CG because it's switching in the opposite direction. So the delay will be more than X. So this is called positive and negative crosstalk. The example is here. The charge required for the coupling capacitance is larger when coupling net and victim net are switching in opposite directions. The aggressor net is switching in opposite direction, increases the amount of charge required. So this is an example of positive crosstalk where this is falling here, and this is rising. The effect is that earlier, in the ideal case, this was the waveform, the dotted line was the waveform, but when the aggressor is switching in the opposite direction, there is a delay because of the charge change at CC. CC needs to be charged from the charge changes 2 into CC into VDD. So this causes a delay, and therefore signal which was arriving earlier is now arriving later. This is called positive crosstalk, right? Positive, why positive? Because it is resulting into an increased delay. Negative crosstalk, whenever the switching is in the same direction, this is the ideal waveform, dotted one, but it will make the switching a bit earlier. This is called negative crosstalk delay. Why? Because it is making the delay less. So it is a negative crosstalk delay. So crosstalk can either increase the delay or reduce the delay. Now this is noise was separate than delay. Although timing window information is coming from the delay part, but noise is resulting into the incorrect logic. But crosstalk now affects us at the whole timing calculation. Why? Because the delay through the nets can be either more or less than the ideal case. Again, This delay depends on the timing window. Same timing in window information that is used for noise is used for crosstalk delay. Again you have A1, A2 and A3 and there is a victim net. Bin 1, A1 and A2 that are switching at the same time. Bin 2 has A1 is switching, whether only A1 is switching, B3 only A3 is switching. So we have the values here 0.12, 0.14 and 0.13. So in bin 1 the effect is the crosstalk delay impact is 0.26. Bin 2 has only A1 0.14, bin 3 has only A3. So the same timing window information that was used for noise is also used for crosstalk delay, right? So this is the timing window information. Now see, here in this case the victim net is static. So this is a noise case. So any switching here, any switching at early arrival will only cause noise. It will not cause crosstalk delay. But now the victim is switching. It is switching, and any switching here, then any switching of aggressor here, when victim is switching, will now cause. Since it's switching in the opposite direction, it will cause it to delay further. Now please remember, the delay is usually from 50% threshold, but now the 50% threshold moves to the right, so there is more delay. Again, if the aggressor switches late, it will only cause noise. So this diagram here nicely captures the difference between noise and blip. If the victim is static, it is noise, which are these two cases here, 1 and 2. If the victim is changing, aggressor is also always changing. Aggressor means that there is some value change. If the aggressor net is static, it is not aggressor at all, right? So any change in aggressor, if it happens when victim is static, is noise. Whenever victim is changing value, then aggressor will cause it to either change late or change earlier. So this will affect the delay. So please be very clear about what is noise and what is crosstalk. So timing verification, now noise is separate analysis, but now crosstalk comes into our setup hold domain because the delays are affected. Any time, any physical effect that causes the delay to change will change your timing analysis, right? Will make it more difficult for you. Timing verification using crosstalk delay. This is computed for every cell and interconnect. In fact, it is a net effect, not a cell effect. But there are 4 effects here. Positive rise delay, rise edge moves forward in time. Negative rise delay, rise edge moves backward in time. Positive fall delay. So in effect, there are 2 rise and fall, just 2 different transition directions. So it's either positive or negative. Positive means delay is more, negative means delay is less. Now what do you think? What will prime time do now? It will calculate crosstalk, but now it will assume the worst case always. Like in OCV, it assumes that in setup case the data path is delayed, has more delay. In hold, it assumes that the data path has less delay. Same happens in crosstalk. In setup analysis, it will make the launch clock path worse than it was earlier before. It will make the data path still worse. What it means is that any crosstalk in setup check, any crosstalk calculation will delay this more, delay the launch clock path and the data clock path more. It will never reduce the delay on data path or launch clock path. It will make the delay more. So now, over and above OCD, the crosstalk will add delay to the setup launch clock path and the data capture path. On the clock capture path, it will reduce delay, right? So again, let's summarize in the figure here. The setup analysis assumes that launch clock path sees positive crosstalk delay, data is launched late, data path sees positive, so that it takes longer for the data to reach the destination. Capture clock path sees negative crosstalk, right? So again, there's a common clock point. I'll tell you how this affects the analysis later. But again, apply the same principle. If you are prime time, your job is to always assume the worst case, right? What is the worst case for setup? The data getting delayed and the capture clock coming earlier. This is the worst case for setup. Similarly for hold, the worst condition is when the launch clock comes later. When the launch clock comes earlier, capture comes later. So launch clock path and the data path will have negative crosstalk delay, and the capture will have positive crosstalk delay, right? So this slide just lists that capture clock has positive, launch and data have negative. This reverse of what happened in setup, right? So again, when we talk about noise and crosstalk, we have to take care of the computational complexity. A large nanometer design is only too complex to allow every coupling capacitance to be analyzed. This is the key here. It is not possible for prime time to analyze every coupling capacitance with reasonable turnaround time. So there are some settings to make this analysis more practical. So there are some techniques. One is the hierarchical design, other is the filtering. So what hierarchical design means is that, now let's say a chip has 20 blocks, 20 individual functional blocks, and at the chip level these blocks are just stitched together. So synthesis also would need you to synthesize every block separately, because a full chip synthesis might not be a good idea, because again it will take a large amount of time, right? So usually what it does is done in industry is that all 20 blocks will be synthesized separately and then stitched at the top level. For crosstalk also, we will do noise analysis and crosstalk analysis individually at each block level. We can do that. So this would mean that this can only happen. So hierarchical design, assuming that for large design, so we can do that noise analysis and crosstalk analysis at the hierarchical design. That means all 20 would be done separately. This can only hold true when this implies that there is no coupling between signals inside a hierarchical block and signal outside the block. This is true for the case where all 20 blocks have separate layouts. So ideally, so that the usual working flow is that first you define what is your functional block. So I say a chip has 20 blocks. Let's say it has USB, it has a CPU, it has a memory controller. So memory controller, CPU, USB, they all are functionally separate blocks, although they have obviously some communication between them. But consider memory controller now. Memory controller is separate functional block. It also would be a separate layout block. It usually does the case. It's a separate functional block. It's a separate layout block. So it would be synthesized separately. The timing, the functional timing would be closed at a block level also. Plus all the noise and crosstalk data would be analyzed at the block level, at the memory controller level, and not at the chip level. Now this memory controller layout, since it's separate, it will not have any coupling with USB or CPU, because they are located in a different part of chip. So this is what it says here. This implies that hierarchical analysis implies that there is no coupling between signals inside hierarchical block and signals outside the block. Now at chip level you can say that all my functional layout blocks are black blocks, and do the coupling analysis only for signals at the top level, right? Many things might be confusing here, what I said, but when you work in the industry, when you start working on design, you will know that, you will understand them better. Right? Now, again, so this third is that this also this goes on the second point, that signal net should not be routed close to the boundary of the block, because if the signal net in a hierarchical block are routed close to the boundary, then the signals outside the boundary at the top level will start affecting, and your assumption that there is no coupling between the block and the outside of the block does not hold true. Right? Second is filtering of coupling capacitances. The filtering is that filtering are usually prime time will carry out. Obviously, there are some variables to control the filtering process. So it will filter out. There's a variable that controls that how a smaller value of coupling cap can be filtered out. For example, below 1 femtofarad, you can filter out the coupling cap. More important than the absolute value is the coupling ratio. Aggressor net with small coupling ratio. Coupling ratio is the ratio between the grounded cap and the coupling cap. If the coupling ratio is very small, they can be filtered out. They can be ignored from analysis. Lumping small aggressors together. Multiple aggressors with small contributions can be mapped to one large virtual aggressor. This is just to, so this filtering is being done at the coupling cap level, right? First two were done at the coupling cap level. Third is done at the calculation level. That means if prime time sees that there are a lot of small aggressors, it will make a virtual large aggressor and it will couple, it will make it a numbed aggressor. So this exact subset of switching aggressors can be determined by statistical methods. Let's not worry too much about the statistical methods now. So how do we enable noise in crosstalk? First important thing, when we read parasitics from a spec, we have to include the switch, keep capacitive coupling. This tells otherwise prime time will ignore the capacitive coupling and no noise data, no crosstalk data will be present. Then report timing has a crosstalk switch, report delay calculation has a crosstalk switch, you can use one crosstalk switch. Usually all delay reporting commands will now have a crosstalk delta switch, where it will tell you, in addition to the delay, it will tell what is the crosstalk. This is a timing report with the crosstalk delay. Apart from, so you have seen the path column, you have seen the incremental column, now there is a delta column also. So see that this is the launch part, these values are positive. So this is a setup report. Why? Because it's a max, it's an asynchronous default group, it's a reset path. So in the data path, you will always see, for setup in data path, you will always see positive values, not negative values. Apart from transition, there is also detrans, which means that so crosstalk affects both. It will also delay the signal and it will also make the transition worse. So it tells what is the detrans, what is the delta transition. This is the delta time. So this delta time is added to the path. This delta transition is added to the actual transition. So the delays will become worse, the transition has become worse. So you can spend some more time in understanding the timing report. Usually the only special thing here is the delta and the detrans. These are the only new things here. Right? Now let's talk about clock relationships. So now see, we talked about timing windows. We saw how noise and crosstalk analysis is affected by timing windows. We saw a few examples where there are more than one aggressor. Now the timing windows depend a lot on clock. In fact, clock is the, so if you have multiple clocks, then your clock relationships will affect your timing windows. Now I mentioned before in one of the sessions that let's say now these two clocks, clock 1 and clock 2, are false to each other. They are asynchronous to each other. Now there are multiple ways of defining this. One is set false path, other is the set clock groups. If you are doing noise and crosstalk analysis, do not use set false path to set false path between two clocks. Use set clock groups. This is the prime time requirement. Set clock groups tells prime time exactly what is the relationship. So there are three switches here: asynchronous, logically exclusive, physically exclusive. Asynchronous means that both the clocks, they are asynchronous to each other, but they are both existing on the chip. What it means that, now let's say, assume clock 1 and clock, assume there is no mux here, forget about this this structure here, assume that there are two clocks coming here from separate sources, clock 1, clock 2, this is let's say this is clock 2 and this is clock 1, and now clock 1 and clock 2, if there are two clocks which are existing on a chip at the same time, they can come from different PLL, for example, and there are two nets which have a coupling cap, and one is driven by, let's say this is aggressor, it is driven by clock 1, this is victim, it is driven by clock 2. If they are asynchronous to each other, it will assume an infinite timing window on one prime time. Why? Because they are asynchronous. Data on one has no synchronous relationship with data on two. So the aggressor will have an infinite timing window. That means aggressor can come at any time. So any transition on two will always be affected by aggressor. Always. This is what asynchronous does. Now let's see second case. Logically exclusive. Now you have this kind of structure. Now clock 1 and clock 2, only one can occur at this point. Only one can come at this point, right? So beyond this point, we have to set clock 1 and clock 2 as logically exclusive. What it tells prime time is that clock 1 and clock 2 are logically exclusive, which means that any crosstalk. So now this X4 is the coupling tab. Now if clock 1 and clock 2 are asynchronous, this would have an infinite timing window. But now there can be only two cases. Once at this point, either it's by clock 1 driven by clock 1 or driven by clock 2. So when it is driven by clock 1 or clock 2, then there will be proper timing windows on this net. On aggressor net and victim net, there will be proper timing window calculation. There will not be an infinite timing window, and effect of X4 will be taken into account, right? But effect of X1 now there can be a coupling tab between clock 1 and clock 2. So this will analyze the X1 effect also, because it is. But now you probably want to analyze X1 also. Why? Because beyond this mux, X1 is before this mux. So clock 1 and clock 2 exist before this mux, right? The physically exclusive is the case where the clock, for example, is coming from outside, and on the same clock port you can have two different clocks. Let's say in one application you can apply one clock to the chip port. In another application, for example, test mode, you can apply another clock to the chip port. Now these clocks are physically exclusive. What it will tell prime time is that it will never launch on one clock and capture another clock in terms of crosstalk. So the timing windows again will not be infinite. There will not be any crosstalk effect, which is special to the two clocks being different, right? They are physically exclusive. They cannot exist together, right? Now see this. If you want, now this is the case. This is a slightly complex case where you want the effect of X1 to be taken care. So what do we do? Right? We do something like this. Even if you don't understand this, don't worry about it. There's a clock 1 and clock 2. We create generated clocks here. We create a generated clock GCLK1, which is divide by one version of clock 1. We create a clock GCLK2, which is a divide by one version of clock 2. Now we set GCLK1 and GCLK2 to be logically exclusive. So there will not be any infinite timing windows. But clock 1 and clock 2 are asynchronous. They are not logically exclusive now. Logically exclusive part is now shifted to GCLK1 and GCLK2. CLK1 and CLK2 are still asynchronous, so crosstalk checking will happen here. So even if you don't understand, don't worry. But take one. The gist is that the clock relationships. I'll just summarize this. The clock relationships are very important for noise and crosstalk delay calculation. If you are doing noise and crosstalk delay calculation, use set clock groups command. Third important point: be very sure about whether the clocks are either logically exclusive or physically exclusive. This is the summary. Actually, I should have a slide of summary here. I'll probably add this later. But okay, so we studied about as the last slide. So we talked about the noise and the crosstalk. Both are caused by the same effect, same physical effect. Noise is the case where victim is static. Crosstalk is the case where victim is switching, and the crosstalk causes the victim net to have a worse or a better transition and worse or a better delay. Since this is the delay part, this will affect our setup and hold timing in exactly similar manner as OCD. For setup, the launch path, the clock path, and the data path will be delayed by more. Have more delay. The capture clock path will have less delay. It will be the other way around for hold analysis. Again, we see that you need to be very good at understanding clock relationships for noise, even for timing. For timing and for noise and for signal integrity. This is the noise and crosstalk combined together. This is called signal integrity. Signal integrity is another term for crosstalk, right? So if you are doing signal integrity analysis, you have to be very, very sure that you have to use set clock groups command for defining the clock relationship in time. It was all for noise and signal integrity. We will not have a lab of this because again we need very good backend data to do lab. So I'll try something. If I am able to come up with a lab, I'll include this obviously. But as of now, I don't have any lab for noise and signal integrity. This is because it's a slightly advanced topic when you consider the limits of this course. In the last session of Unit 5, this was the second last lecture session of Unit 5. in the last session of Unit 5, we will study about the. I'll give you some introduction about the statistical. Thank you.